Now let me take a general equation and analyze few things. Say we have A plus B giving C plus D such that it is a reversible reaction and C plus D gives back A plus B. So maybe I'll write it separately over here that C plus D gives back A plus B. And on balancing, we have a certain stoichiometric ratio. Suppose that was A, B, C, and D. A amount of A, B amount of B, like 2 amount of A and 3 amount of B, something like that. C amount of C and D amount of D. So while writing back, the stoichiometric ratio would be same, obviously. So it is C, this is D, this is A, this is B. Now, again, I would like to ask you to just see whether you got it right or not. Your rate of the above reaction, I'll just call it as forward reaction, rate R forward. Now, what do you think? It will depend on A, B, C, or D, or all of them? What would it depend on? It is going to depend only on the ingredients, only on the reactant, only on the reactants. That is, it is going to depend on A, in fact, the amount of A, and is going to depend on B, the amount of B. Now, it would be a certain function of A and B. So I'm going to write the function in a while. But let me ask you something. Say the reaction was P plus Q gives whatever, because what is getting formed is immaterial in getting the rate. So I'll say the rate was proportional to P times Q, the amount of P into amount of Q. If this logic is right, in fact, we are going to study the rate law. The rate law tells what the rate would be, and that is going to be in chemical kinetics chapter next year. So I'm not going to get into details of that, but I'm just saying that if this is right, if it's the multiplication of concentration of P and Q, then had it been R plus P plus Q, then would the rate law or the rate not proportional to this? Yes, it would be by going by the same logic of P into Q. And now let me replace the R with another P. So if there are these are the three molecules which are say bombarding among themselves and forming the product. Where is the issue which we are going to study next year? So if suppose that is happening, then would it not be that the rate will be given by P into Q into P again? So if I write P into Q into P again, then that mathematically is P square into Q, right? So going by that logic, what do you think would be the rate of this reaction given over here? The rate of the reaction is given by A power A and the concentration of B power B. In fact, if I have to go uh, uh, by the law itself, by the rate law, then I should be writing the activity over here. So instead of concentration, it would be small a, which is activity of A, power A, activity of B, reactant B, power the coefficient of the balanced reaction. That would be like in the minimum integral form. That's the standard way of writing it. So the rate will be proportional to that, where A is activity and B is activity or active mass. In fact, active mass. Now, what active mass translates for us in this particular chapter is the concentration for things which are in a solution, or even in gaseous form, you can say the concentration, moles per unit volume. Now, if I look at the formula, PV is equal to nRT. Your moles per unit volume, which is your concentration, can also be represented by P, because your R and T, all of this is happening at a certain temperature, is a constant. So the activity of gases can be written in terms of pressure instead of concentration moles per volume, but we are going to come to that. Hence, I've just written concentration over here. You might write the pressure also if it is all gases, if these are gases. So that's the rate forward. And if you have to replace the proportionality sign with the equality sign, then the rate forward is equal to rate constant, which is written by small k forward, A power A and B power B. Now going by the same sense, if C and D had to react and give A and B, so here these are the ones who are the reactant, what would be the rate? And I'll call this rate as rate backwards, even though the rate is written, it is forward over here, but we know this is our original equation, and hence I'm calling this back formation as rate backwards. So the rate reverse or rate backwards is going to be proportional to the concentration of C, concentration of D, but there are C times C over there. So concentration of C power C, concentration of D power D, where D is the stoichiometric coefficient, and the proportionality, instead of proportionality I've written an equal to sign. So that means I can put the constant to remove the proportionality, the constant of proportionality, which is called rate constant, backwards. Now, the individual rate is what we are going to study in chemical kinetics chapter next year. There we'll delve much more deeper. That means we are going to see what is the molecularity of the reactants, what is the mechanism of the reactant or proposed mechanism of the reactant, what might be the subdivision of this or steps of this reaction. All these we are going to study next year. So this year we don't have to concern about how we get this, but we have to concern ourselves with equilibrium, which means that your rate forward is going to be equal to rate backwards when equilibrium is reached. So this is the case what we are going to study. So if that happens, if my rate forward is equal to rate backwards, then what we get? What we get? Rate forward was K forward, A par A, B par B, and the rate backward was K backwards, C par C and D par D. In a while, I'm just going to omit writing the square bracket because it is because I'm feeling a bit lazy about it. By the way, this K I have not written. It is called rate constant. Rate constant. So if I rearrange this, what do I get? If I rearrange this, what I get is K forward by K backwards is equal to C par C, D par D. Pardon me, I'll just not put the square brackets, or I might. Let me just put it. Now, K forward and K backwards, both were a constant at a given temperature, constant at a, so both were a constant at a given temperature. This ratio is called equilibrium constant, capital K. This K is called the equilibrium constant. So this is, it is a constant irrespective of what is the concentration of C, D, A or B. It is a value which is always same at a given temperature. The K never changes at a given temperature. So this is what we are to play around with, and based on numericals in this chapter on. So let me just ask you one thing to make this concept clear. So suppose there's a hypothetical reaction at equilibrium, and it is given that at equilibrium the amount of A is 1, amount of B is 2, and amount of C is 4, amount of D is 2 again. Assume it is happening at T temperature. The volume of the vessel is 1 liter. 1 liter is the volume of the vessel. So what would be the equilibrium constant for the reaction at that given temperature, at this temperature? What is the equilibrium constant? So what would you do? So you can pause the video and do it yourself. So I hope you have done it. I'm just going to write the formula. What we'll have is, in the numerator we have products C and D raised to the power of their coefficients in the balancing, and in the denominator we have A and B, B power 3, A square, concentration of C, concentration of D, concentration of A, concentration of B. Now the concentration of C is 4 by 1. That's the concentration of C because it is in a 1 liter vessel. The whole thing is in a 1 liter vessel. The concentration of D is 2 by 1, so I'm not going to write the 1, and raised to the power 2. Concentration of A is 1 raised to power 2. Concentration of B is 2 raised to power 3. And what we get? We get a 4 into 4, 16 by 8, which is a 2. So our equilibrium constant, and we can write it as a Kc because we were taking concentrations. As I told earlier, we can take pressures if things were gases. Here it is to depict that we have taken concentration. You can write it as Kc. If you don't write anything, it is assumed on the structure of the question what you would have taken. So Kc in this, as moles were given, 1 mole, 2 mole, 4 mole, 4 moles and 2 moles, it will be assumed, even if we are writing K, it will be assumed that we are talking of Kc. So we got this. That's my first question. Now let me just give a second question based on the same reaction. It's the same reaction. Now somebody is performing the reaction somewhere else at the same temperature as earlier, and he says that at equilibrium, when nothing is increasing and decreasing, at equilibrium it is 1 mole, 2 mole, 4 mole and 2 mole for the first guy. For the second guy, he says at equilibrium the concentration is, the amount of molecules are 3 and 2, which eventually is the concentration because the volume of the vessel is 1 and 1, and D is what I am asking you to find, that for this guy what would be the amount of D. He's saying that he's performing the experiment at the same temperature in same volume, 1 liter vessel. So what would be the value of D? You're seeing that these numbers 3 and 2 and 1 has nothing to do with the coefficients. It has nothing to do with the earlier values. A was quite less, C was quite high. This time I've taken A as high, C as less. Will it reach equilibrium? Yes, it is going to reach equilibrium because uh, in fact, in this question, it is already given it is equilibrium. If D was nothing, still it is going to reach equilibrium by doing a reaction in the way it has to be, it has to go. So the question is, what is the amount of D? So everybody pause and do the video. So I hope you have got the answer. Again, we are going to follow the same formula. The formula is same. This time the K value is known. Why is the K value known? Would you say that K was from the previous reaction? How can I use the same K? Mind you, this K is called equilibrium constant. No matter how many times you do the reaction, no matter what are the ratios, what are the number of moles, what is the concentration, the K is going to come same provided it is the same temperature. So K is a constant, and that is what I wanted to emphasize. So K value is 2 over here. C power 1, D power 2. C is given as 1, 1 power 1. D is to be known. So x square divided by your A is 3, 3 square, and your B is 2, so 2 cube. So that's the equation. You can easily cross multiply and get the answer. So in this particular case, the answer would be x is equal to, you have 2 square into 3, which is 12. So X is going to be 12 moles or 12 moles per liter. So that's your answer. So I hope you got the point that once K is found or K is given, it remains same unless until temperature changes. And in this chapter, most of the questions, 90%, 99% of the questions, we don't have a temperature change. When there is a temperature change, how K will vary, we'll have a separate formula for that towards the end of the chapter. So I hope you got a basic idea of how to use K value. Let us just increase the level of questions a bit. In fact, let me ask another question on the same concept, on the in fact the same equilibrium, to have our concepts rooted well. Say the amount of moles of A, B, C, D were 2, 2, 3, 4. What do you think? Uh, uh, is the reaction at equilibrium, or is it going forward or back? Is it at equilibrium, going forward or back is the question. Please pause and give me an answer. So I hope you have analyzed and done it. Again, if we do this calculation blindly, that assuming that this was at equilibrium, assuming 2, 2, 3, 4 is again an equilibrium situation, what do we get for a Kc is, I'm not going to write it as Kc, I'm going to write it as something else if it is not coming. So I'm just not writing anything over here. Assuming it was at equilibrium, if I do it, what do I get? I get a 3 power 1 into a 4 power 2 divided by a 2 power 2 into a 2 power 3. So how much is that? We have a 4 square, which is 16, and that gets cancelled with the 8 and a 2. So we are left with 3 divided by 2. So our value is coming as 3 by 2, which is 1.5. This is not equal to Kc for sure, because Kc is a constant and Kc was equal to 2. We have calculated nothing on this earth is going to change that value except for changing the temperature. So we can clearly see that it is not Kc. So I'm not going to write a Kc over here. I can't write a Kc because Kc is 2 and it's known. They're asking whether it is at equilibrium or not. We can't assume it is at equilibrium. They have given that this one was at equilibrium. We safely wrote as Kc when we are using these values. So this is called Q, which is reaction quotient. So this guy is reaction quotient or Q. So if the reaction is not at equilibrium, it is going towards one side more than the other, it has not reached equilibrium, that time the same calculation, the same product of the products divided by the product of the reactants, that kind of calculation is called reaction quotient. Now let us see whether it's going to go forward or back. That was the other part of the question. So you may again pause the video and reply if you have not already. So you have to tell whether it is going to go forward or back. And the answer is, since the reaction quotient is coming less than K, here Q is coming less than the Kc value, it indicates that the numerator, the Q formula, will also have the products on the top and the reactants on the base. So these are the products. So if Q is coming less than K, that means the product is not enough. This is, the denominator is higher, the numerator is lower. That means C is not enough. Meaning to say, the reaction has to go still further. It has to go further. So the 2 is going to go down a bit. This 2 is going to go down a bit. This 3 has to go up a bit. 4 has to go up a bit in the ratios of their balanced reaction. So it is going to go, AB is going to go down, CD is going to go up, so that the numerator increases, the denominator decreases, and this value 1.5, such that the Q value 1.5 goes up a bit and matches 2. It becomes 2. That time it would have reached equilibrium. By the way, as it is approaching equilibrium, the rate of exchange, the rates become so close that the ingredient increasing and decreasing, that becomes very, very slow, and hence it doesn't pass the value. It just reaches, or one can say it takes infinite time to reach that equilibrium value. So guys, do another quick one. Here SO2 Cl2 gas is giving SO2 plus Cl2, giving or taking, I don't know, it is a equilibrium question, and the equilibrium constant is given to you, that is a 0.0032. The whole thing is taking at a certain temperature, and we have nothing to do with the temperature now. Just to inform that Kc value, it's actual reaction, so they have to give you actual Kc values. So they have given the actual Kc value for a certain temperature, so it can be a factually correct data. Now what they are saying is, if at a certain time all the ingredients have the same concentration, which is 0.05 moles per liter, that means what is given is your SO2Cl2 concentration is equal to SO2 concentration is equal to Cl2 concentration, and which is 0.05 moles per liter. Then you have to comment whether which reactant, which of these species is going to increase in concentration and which one is going to decrease in concentration. So pause the video and do it fast. So I hope you got the answer. Again, going forward, we have to do the same thing. Since all concentrations are given to you, we can't be finding, when we are doing the formula of product divided by the reactants product, that means SO2 power 1, Cl2 power 1, and SO2 Cl2 raised to power 1. This, when we are putting these values of 0.05, then the left hand side will be called Q and not K, because we are not sure whether it is at equilibrium or not. So when we do that, what do we get? We get a 0.05 into 0.05 divided by 0.05, which is a 0.05. Now we'll compare the Q to Kc, and clearly your Q is coming greater than Kc. It is coming greater than Kc. It indicates that the numerator is higher than what we want. The denominator is lower than what we want. So what is going to happen is the reaction is going to go backwards more. It is going to go backwards more and at this current stage, such that these values reduce and that value increases. such that your 0.05 reduces and reaches a 0.032. And for that, what calculations we have to do would be the next thing. So right now I just wanted to know what is going to decrease and what is going to increase. Your SO2Cl2 is going to increase and these two guys are going to decrease. I hope this is very clear to you. So what we have formulated is when your Q is equal to K, that time when your reaction quotient is equal to the equilibrium constant, that means we are actually studying the situation at equilibrium. Certain reaction is happening, A gives B. We are studying this. When this happens, it is actual equilibrium. Both arrows same length you can depict. It is at equilibrium. Now suppose Q is greater than K. It shows that the product is more and the reactant is less, and hence the reaction has to go backwards to reach equilibrium. The forward reaction is slower. The forward reaction is lower. The product is more and has to go backwards. So it shows that the reaction will go backwards. And similarly, if Q is less than K, capital K, mind you, equilibrium constant is capital K, and small k we were writing for reaction rate constants for the forward and backward reaction separately. So now again, if Q is less than K, that means your products are less, your reactants are more. Your reactants are more, your products are less, and hence your forward reaction would be at a higher rate than the backward reaction. So the reaction is as a whole, the reaction is going forward. So there's a graph of the reactant quotient Q over here. Now you can see if the graph has been drawn if there was only the reactants initially and nothing over here, no products. So the Q was 0 because there was no product divided by enough amount of A's and B's. So that starts with 0, but as the product starts forming, you have the numerator building up and this one going down. So the Q value increases, and eventually the equilibrium is reached, and at that time the Q value becomes the K value. You can pause the video and study this. No great deal over here.